So I would like to examine one of Gauss's law that relates to the electric field. What Gauss has said about the electric field is that the change in the electric flux, which is an I with a circle through it, sub E, is basically asking how is the electric fields that are permeating some sort of 3D symmetrical surface, how is that changing? How is that changing at all? Well, that's equal to the closed integral of the electric field enclosed, of course as a vector, dotted, not multiplied into, dotted into the derivative of the area vector. All right, so we have this, and that's also equal to the charge enclosed over permeability constant. That looks like a backwards 3 with a sub-zero in it. We don't need to worry about that too much. That's just a constant number, 8.85 times 10 to the negative 12th over Coulomb squared, newtons times meters squared. But we're not going to worry about units too much here because this is just an example to examine something. We don't know the units of the area vector in this case. But, so we have a constant number here. We just have this constant number. We're going to leave it on the other side for right now though. Let's draw a shape. So Gauss's law here applies to a 3D shape. Let's pick a nice shape like a sphere, a 3D sphere. So I've drawn this point at the middle. We don't know. It could be a positive or a negative charge. That's the charge we want to find that's enclosed. Well, let's say we have some electric field lines, for example. Electric field lines. Let's say the field lines of this charged particle are pointing radially outwards infinitely. They're permeating the surface of this sphere here, going all throughout it. Of course, there's not just going to be 8 field lines in a real life scenario. They're going to be everywhere across the surface, pointing everywhere out of the page, into the page, because this is a 3D surface. Well, now we have to find where our area vectors point. Well, the way I think about it for a sphere is finding the area vector direction it points in is if I was trying to increase the size of this sphere, say out to here, the radius out to here. We want the radius out to here maybe. Well, my sphere sides would have to go this way. So our area vector is pointing radially outwards as well, all across this surface. So it's pointing in the same direction as the E field. So now we can talk about this dot. What does this dot mean? Well, that means that the closed integral E area vector, it wants you to multiply the derivative of this area vector, these two vectors, because they're both going to be pointing away, times the cosine of the theta between them. Theta. Well, what is theta in this case? Theta is equal to 0. The line between the two points in the same direction. We have our E vector and our A vector right here. They're pointing in the same direction. The angle between them is 0. So that means cosine here, since our angle isn't changing between the two at any point, and we assume that the charge inside is not closing, we can pull both of those outside of the integral. So we get that our electric flux is equal to E times cosine of 0 times the closed integral of dA. Well, let's clarify something really quick. Electric flux is not an area vector, or it's not a vector. It's just the magnitude. So just once the magnitude of these, it's not going to end up as a vector. So this should simplify to the electric flux is equal to E times, well, this is going to simplify to 1. Cosine of 0 is going to be 1 times the derivative of integral, which is just the area. So it's equal to E times A. We know both of these, hopefully, if we want to find the charge enclosed, that is. So we do have our Q enclosed. We don't know what's inside. It could be positive, it could be negative. This is some sort of positive or negative constant. This is just our area function. Area of a sphere, is 4 pi r squared. over our permeability constant? Well, we know our permeability constant, we know our E, we know our A, so let's just bring this to the side. Let's multiply by permeability. So we end up finding that in this Gauss's law equation that the electric flux is equal to E times A times permeability is equal to the charge enclosed. So this is going to be a positive or a negative number. If it's positive, we have a positive charge enclosed, like a proton. Or if it's negative, we have a negative charge enclosed, like an electron. So this isn't too relevant to real life scenarios, but it is helpful for using the symmetry of nice 3D shapes and the angles between them. We can easily find some sort of mystery charge enclosed. Like if you're an engineer and you want to know the charge within something, whether it's positive or negative, you could easily find that if you have a perfectly symmetrical thing like a sphere, and you get that it's just equal to the electric field times the area times the permeability constant. Of course, these are going to be. This always has to be positive. You can't have a negative area. This is always going to be positive. And what it depends on is the electric field going through it, whether it's positive or negative. That's really going to be what determines what kind of charge is in there. So, since our electric field is pointing out, then only positive charges do this. So if we were given a positive number here, we have positive times a positive times a positive equals positive charge enclosed. And there you go.